Hey, my name is Baris. I'm a graduate student in physics at University of Wisconsin-Madison. I will talk about how we can speed up the quantum adiabatic algorithm for random spin systems. So here is the QR code and archive identifier, if you are interested. I did this work together with Bob Joint and Maximo Willow. Yeah, so this is a great place to talk about topological effects. We have some Berry court, Berry drive, some Berry connections. So we are at the right place to talk. I'm at the right place. So a little bit background, it's possible to derive the ground state. We know that if it is non-degenerate, without any transitions in a short annealing time, it is based on the transitions tracking algorithm. It is a work done by Michael Berry. It's a method of shortcut to adiabaticity. We can write the algorithm for ground state. So H1, and we have H0, the original Hamiltonian, the usual annealing, and together the total Hamiltonian H0 plus H1 derives the ground state without transitions under certain conditions, which is ground state should be non-degenerate. And the derivation follows from canceling the Berry connection in the interaction picture. Then the Hamiltonian becomes diagonal, and we don't have transitions to excited states. Can we apply this idea to random spin systems? Shortcuts to adiabaticity in general, and especially this transitions tracking algorithm I'm going to talk about. So we can choose H1 as the steering Hamiltonian, and let's see how we did. We will try to solve the H final Hamiltonian, one-dimensional Ising model with random field in z direction. It's a closed chain. Here is the sketch. The red arrows shows the spins, and blue is the random magnetic field. J is constant. So H0 is the usual way. And we have the time schedule. We choose it so that the steering Hamiltonian and H0 is starts and stop slowly. And we have tau, which is t divided by ta. It changes from 0 to 1. At the end, we will do exact diagonalization and compare the result with the Schrödinger equation solution simulation. So to start with, if we have only one spin, there is no interaction. This is the same as many spins without any interaction. And we start with a large H0, and the direction changes to z, and H final is something smaller, and it's random. It can be in plus or minus c direction. Our selection is from minus w to w, uniform distribution, H final, and in general for larger systems hi. And the time unit is h bar divided by w. H0 we choose 10 and w is 1, so hi is from minus 1 to 1. And we took 10 to the 4, we performed 10 to the 4 realizations. Here is the average ground state probability as a function of annealing time. We need to wait for a long time to reach ground state probability 1, to be 1. Yeah, we calculate the ground state probability of one realization, which is overlap squared. Let's compare this with if we apply the steering, which makes the Hamiltonian non-stochastic, b cross b dot divided by 2b squared, which can be calculated using the transitions tracking algorithm. So we have x, z, and y directions now. The steering Hamiltonian can be calculated. It is 0 at initial and final time, and it has non-zero value in between. And we see that if we have, even if we have short annealing time, the average ground state probability is 1. So this is not so unexpected. Let's look at a larger system, which can also be basis of a cluster approach that I will present in the final part. And we have interaction and open chain interaction between each spins. J, interaction constant, let's take it 0.1, relatively small. But it's, I will also compare it with larger values in the next slide. So HI is the initial Hamiltonian. In the x direction, we have a field on each spin, and H final, we want to solve this Hamiltonian. Random field HI, H2, and H3. If we apply the one-spin steering, ignoring the constant parameter J, then even at short driving time, we can increase the ground state probability. Ground state probability. So from 20% to 80%, we can increase it. And if we apply the full steering, which is the exact formula, then always we get 100%. But the easier way is one-spin steering. And even at short driving times, we can increase the ground state probability to a much larger value comparing to without steering. So I show the value for J.1. J.1, what happens if we fix the annealing time equals 1? If we change J from 10 to the minus 3 to 10 to the 1, then up to J equals 1, we can increase the average ground state probability if we apply the steering, one spin or full steering. And for larger J, the unsteered algorithm performs slightly better. But yeah, if we keep J smaller, it's possible to get much larger probability. Let's apply this idea to larger systems. Yeah, as I said, we are trying to solve the one-dimensional Ising model with random field in z direction. We observe a similar speed up if we apply one-spin steering for system sizes 8, 10, and 12. It's possible to increase the average ground state probability from much smaller values to closer to 1. So these values are around 1 divided by 2 to the L, and it's possible to increase for these system sizes closer to 1. Yeah, J is 0.1. So to reach at the level of one-spin steering, we need to wait until TA equals 100. So we can also calculate values such as ST99, etc. So we will find that for these values, we can get around 100 speed up. Let's again look at the J change. J is varied. We can see that the ground state average probability is not sensitive to L when J is relatively small. And when J is around 1, the low-lying eigenstates are extended and they are entangled. For the local minima, which are due to extended states, unsteered algorithm is slightly better. And if we increase J, then in this case, the steered algorithm can reach the unsteered algorithm when J is larger. And the reason might be the ground state can be written as product states approximately in that region. But if you look at J smaller than 0.4, then we can increase the average ground state probability significantly. Let's look at probability distribution. Here, we don't have continuous distribution. We have 2 to the L for each system size levels, and levels are ordered in the order of increased energy. And if we apply the steering, it's possible to find the ground state. In both cases, we find the ground state most likely in the ground state. We find the final state most likely in the ground state. But if we apply the steering, it is much closer to 1. There is around 10 to the 2 increase in the average ground state probability. And we can also see in the inset that almost all the probabilities are in first 10 levels if we apply the steering. And the distribution is more flat if we don't apply the steering, but we have more steep distribution here. So it's possible to find either ground state or other states in the first 10. Yeah, let's look at another distribution, this time cumulative distribution. Yeah, average ground state probability, we have 10,000 realizations, and more than half can have a value closer to 1. And if this time, if we also include the excited state, here red is if we apply the steering, blue is steering off, and P1 plus P2, we don't see the clusters, the red small clusters. And if we look at the larger cumulative sizes, then at the end we get 10,000 realizations closer to 1, but green is only moved to the right a little bit. It's barely passes 10 to the minus 2. So here, even the ground state probability, we can get more than half closer to 1. Yeah, the bad side of this steering is we have some clusters in smaller values. So there's some localization issues. Here for j equals 0.1, if we don't have steering, then the maximum PN distribution this time is much smaller comparing to if we turn on the steering. So we don't know which state we are at. We are just looking at the maximum PN. Then if we turn on the steering, then the minimum max is larger than 99%. This means that the state is localized in a certain state, certain eigenstate in the final time. And some final states are favored. We have less diffusion when the steering is on. Yeah, so this distribution shows us that first a few states have almost all the samples results in the first a few states. So if we have steering for certain J and TA values, it is possible to find the ground state probability for more than half of the realizations. Yeah, the final thing is I want to present is a cluster approach, and here the troublemaker is the spin with the lowest, smallest magnetic field. Let's say this is H2. We can form a cluster such as H1, H2, H3 together because the dynamics is governed by the neighbors. We can consider a trio of these spins, and to the rest we can still apply one spin steering. So what happens for driving time 1, 2, and 8? Even the driving time is large this time. We looked at 1 previously, now 1, 2, and 8. This time, again, without steering, we have 65% probability, but if we form clusters, we can even get much larger, especially when J is small. We have a flat curve here. The decrease rate is smaller than one spin steering. So cluster can provide even more ground state probability increase. So the summary is For short annealing time, we can derive the random spin systems, not derive. Using some deriving methods, we can find the ground state of a random spin system with relatively weak interactions. And a less local form I provided, the cluster approach, can increase the ground state probability even more. So yeah, this method may not be better for metallic phases, but for insulating phases, for short deriving times, it's possible to get large ground state probability. I did the simulations using high throughput computing, using the resources of UW Madison Center for High Throughput Computing. Thanks for listening.
Thank you very much. Yeah, we definitely have time for some questions. So.
Hello. For these sort of short run times, how big does the magnitude of your steering term get? Does it get very large, or?
You mean H naught, or?
I mean the part of the Hamiltonian that's doing the steering.
Are you talking about does energy gap increases?
Well, yeah, the sort of prefactor in front of the parts that actually do the steering. I was wondering, with the short times, how big does that get?
Yeah, for one spin steering, well, we can find the maximum of this function.
Right. So,
yeah.
I mean, it seems like an interesting natural
actually,
restriction would be to sort of cap that and see how well it still does.
Yeah. We can choose different H naught. I fixed H naught at 10 and check what happens at ground state probability.
Right.
And we can also study energy gap. I studied a little bit, and I see that at the final part, the steering increases the gap at the final part of the annealing. Okay. I may provide more figures maybe later.
So staring at this formula, is it on?
This or?
Yeah. So it looks like you need to be pretty fine-tuned to get this Hamiltonian. Have you checked how robust it is to not getting this exact form?
You mean?
So what if your prefactor for sigma y is off by, I don't know, 10%?
You mean if H naught is not 10 but 1, what happens, or like?
For example?
Yeah, in general, okay. Yeah, in annealing, the unsteered algorithm starts with a large H naught, but if we keep H naught small, do we still get large probability? Yeah, I should have asked this question, and I will look at this. Yeah, thanks for the question.